Are you sure you can hear him?
I swear. Tell Guy that he missed the quizzes. Yeah,
Okay? I know. Yeah, no. She told me.
So, guys, let's start. Hi, my name is Arya Shadi. I'm going to be your TA this semester. And so, let me introduce myself. I've been here in Texas Tech for 3 years now. I've been working with Dr. Equity, and I was the TA of Dr. Yamani before. I had a wonderful experience working for him. So let's start. So before going through the discussion and the slides, let me give you an overview of what we're going to talk about today. So first, everything today is about reservoir performance prediction. And by that, we're going to divide it into two sections. One is analytical solution, which is mainly for single-phase flow, and the other one is multi-phase flow, which gas is involved. So we're going to talk about Vogel Equation, and we're going to derive some equation ourselves, and then we're going to solve two examples. That is basically cover what you need from the Vogel to the end of your bachelor's. Okay, so when we talk about reservoir performance evaluation, what do you guys think? What is the parameter that you want to know from the reservoir? Maybe. What is it? Pressure. So basically, if you have the pressure distribution in your reservoir, okay, then by Darcy's equation, you can relate it and actually solve it for pressure distribution. Okay? So, I brought some of basic equations that might not seem familiar to any of you guys, but I thought it's important to discuss. So, you've seen those single-phase flow equations. Have you ever asked yourself, where do they come from? Have you asked yourself, is it empirical? What do you think? It is not empirical, because as you see, it is related to Darcy's equation because it has permeability. So as far as you know, it's analytical. But where does it come from? Okay. So the derivation is not hard at all, but I'm going to give you just a quick path as then how it is being derived. So when you talk about mass and when you talk about energy, both these parameters can be related through material balance. Can you tell us what material balance is? Okay, let me start off first. So material balance is if you have a closed space, like a cubic, whatever goes in comes out, plus the accumulation within that cubic, right? Does it make sense? Or you can produce mass. No, you can't. It's the same as with energy. Energy goes in, okay? It's going to accumulate, and it's going to go out of it. This simple concept, okay, can help you to come up with a derivative or partial differential equation, which is this equation that you see over here. So you have a closed cubic of space. You can call it as a part of reservoir, and you can say whatever mass goes in goes out plus the accumulation of mass within this cubic, and you can write it this way. So basically, it tells you, okay, in all directions, whatever goes in goes out, and this is the accumulation term. Simple as that. I don't want you to know, and I don't want to teach what are these variables are, but I can tell you this is rho, which basically means it is mass. So this is a mass balance equation. It's no more than that. It is what you start your reservoir engineering from, and reservoir equations. So this is velocity and this is your density, and velocity is related to the pressure. This term just imagine pressure, and you can write it down. And if you simplify it by many simplification and assumptions, you come up with these equations. Still, it is not remotely related to what you have seen in your many courses. So let's say from the simple equation of material balance, get to this equation, which is the second partial derivative equation as a function of direction and location and time. So if you solve that equation, which is solvable, you can get the pressure distribution. It means at time equal t0, you can tell the pressure at the location of x, y, and z. Is it clear? But this equation that you see here requires a numerical simulation, numerical approach, as you see. What is the numerical approach? We have an eclipse. So the eclipse that you see is not the analytical solution that you guys are using. Basically, how many of you know what eclipse is? You guys know?
Software.
Is it a software that tells you a lot of reservoir characterizations within the reservoir? Characteristics within the reservoir, and the most important is pressure. And many people are using it. This actually is how you can estimate and predict your reservoir performance. So this equation that you see here is solved numerically. Then you don't want to have many assumptions and you want to solve it more realistically. I told you, now we're talking about mass balance. We can also have energy balance, which instead of heat is going to give you temperature. Okay, in one of my courses that I took with Dr. Ekery, so I solved this equation in a 2D. It means I neglected this term. So I solved this equation just for temperature, and as you can see, the pressure is supposed to propagate from the heat source, which is up there, and it goes down. It actually increases the temperature of the whole rod. This is the copper rod. Okay, make sense? You have a relation, which is shown over here. You solve it numerically, and you get the temperature distribution. It's the same for the pressure. So now we're going to get into the equation that you guys have known. When you have this equation, you further simplify it and make some assumptions. These are the assumptions that we have. It has to be single phase flow, homogeneous and isotropic reservoir rock, slightly compressible fluid, negligible gravity forces, temperature should be the same everywhere, and horizontal laminar flow. If you have these assumptions, by some simple mathematic manipulation, you can simply get to your equations that you know, which are these equations. You are familiar with the steady state, and transient flow. Okay? So, before going further, I just want to give you guys this knowledge that reservoir engineering is just a material balance. You have a very small closed space that you apply the material balance and derive the equation. Now you can solve it for very huge reservoir and get the pressure at all the distances and all the directions. Yes?
Is this posted on Blackboard?
I'll put it after the class.
Oh.
I usually put it after class. So I just want you guys to know about this. So now that you have these assumptions that I just showed you, is it single phase? Is it homogeneous? Okay. We are actually thinking of a reservoir that it could not be real, but could give a good approximation if we have a handy analytical solution. So in this session, all we talk about is the IPR curve, which is the performance of reservoir. We're not talking about tubing reservoirs. So let's move to the equations that are not going to be the main focus of this session, because we're going to talk about Vogel and we're going to actually solve equations and solve the examples for Vogel. But as you can see here, I've put all the equations in hand, so you can access it through just one slide. So with your pseudo steady state curves, based on the time, you have different average reservoir pressure. That is going to dictate what will be the IPR. Let's say the transient, but this time time. And also steady state as a function of skin. Okay? But so do you have any questions as of right now?
Yeah, what do you mean you say as a function of skin?
Okay. You have one line, right? You know what skin is?
Yeah.
Okay. This one line, it depends on the Vogel condition as well, which is quantified by your skin factor. When the skin factor changes, that equation changes. So your PWF is going to change. So the curve will deviate from that one line. I put a variable for transient as time and for pseudo steady state as average reservoir pressure. So this is single phase flow, okay? How likely will it be to have just one single phase in your reservoir? Unlikely, right? So you have gas. So when gas is introduced in your reservoir, everything gets complicated. I'm not exaggerating because it will be the case. Okay? So an analytical solution might not be the answer now, because not only your pressure is not going to be Darcy flow anymore. Also, if you want to use Darcy, then you have to introduce the permeability, gas phase, water phase. Everything is complicated. You cannot actually have it within one equation. So let's flash back. I introduced you to the mass balance and mass rebalance equations. If you use those equations and solve it numerically, okay, you get the right, absolutely right answer. If you absolutely right analytical answer, if even you have your gas. But it's not the case. So what is the solution? The solution is Vogel's equation. So let me ask you this. Is Vogel empirical or analytical? Empirical. It means that you can do many assumptions thinking that all reservoirs performance is just a function of simple parameters that you see over there. That's where Vogel equation comes to play. Okay. So let's talk about this curve. So first of all, when you want to actually draw your IPR curve, okay, your PWF, okay, is going to go down. So this is what I mean. Your PWF is over here. So when you're going down, the pressure is decreasing till you get to zero, which is going to give you the absolute flow rate. So at some point you're going to pass the bubble pressure, right? When you pass the bubble pressure, gas has already been evaporated. That's why you should know Vogel to be able to draw your IPR curve. It's not optional. You have to know it. So that's why today, okay, I'm going to talk to you about two examples that we're going to go through, and you have to write it down. I'm going to write it on the screen, and you guys can write it on the paper. So simply, it says flow rate is a function of maximum flow rate, which is kind of this guy, and it is also your P bar, which is the average pressure of the reservoir, and PWF are the two other parameters that are involved in Vogel's equation. One thing, if in the future you take nodal analysis, they're not going to teach you properly Vogel's equation. But you're going to have a question in your final exam, and the equation will not be given. You should memorize the equation. Okay? Vogel's equation. So which one? So I'm not talking about this one. Okay? But you have to memorize this one, or either this one. These two are the same. Memorize the equation. It's simple. But as far as I helped Dr. Heimsey, that's the only class we had Vogels. I remember they were expected, students were expected to know the Vogels and memorize it. Yeah.
So basically you said the vocals is for two-phase, right?
Yes, let me help
Okay,
you.
but you didn't mention something about reaching the vocals more pressure.
Mhm.
So how we using vocals equation after this point, right? Is that what you're trying to say? Is it vocals
Okay.
after vocal point?
Okay. Then you use Vogel. Okay. You assume that it has already passed the bubble point.
And that's the
Okay. Yeah. So you see, he brought a very good point that when should you use the Vogel's equation. Okay. It simply says when you have two-phase flow. That's completely correct. But when you draw the IPR curve, okay, you might start from an equation up there, which is well above your bubble point pressure, right? So this is your RPR, this is the PWF, and this is your average reservoir pressure. So average reservoir pressure is at this point, and so basically you're not going to have any pressure above your average reservoir pressure, and your PWF is going to start from here to here. So, but your PB, or the bubble point pressure, is here. So this point, is it single phase or multi-phase flow? Single phase. Okay. How to draw this line? Like what equation you should use? The one that was shown before, right? So okay. When you talk about this, you know, index factor, PI, productivity index factor. Okay, it's simply the slope is the same as the slope of this line over here. So everything starts from the time that you reach the pressure over here, and natural phase flow happened that you have to use the Vogel's equation. Okay, is it clear now? So you might be given, or you might be asked to draw Vogel's equation, even though the beginning of your pressure is the average reservoir pressure. So you know that, okay, I'm going to go till I reach the bubble point. I'm going to use those analytical solutions for the productivity index to get that straight line, and then I'm going to start to go. What is it? Okay.
Max flow,
Qmax. Don't get confused. If you Qmax, if you have, let's say this line, it starts from bubble point. Okay, you're not in the single phase zone. Okay, so if that's the case, this is going to be your Qmax. Okay, when the pressure is 0, will not be the case ever, because you have the hydrostatic pressure of your tubing. If it is 0, of course you have the highest flow rate, right? That is called Qmax. Okay. So let me give you this fact that the above equation is completely used, is easy to use if your P bar, or average reservoir pressure, is below bubble point. What if it is above? Okay. If it is above, some other factors that are going to come into play, QB and QA. So this is going to be ultimate Qmax. Okay. However, the section that is above the bubble point is going to be called QB, and the one that it is after the bubble point is going to be QA. Okay? Put that in mind. So, I'm going to go through some derivation while that screen can be
Last equation, the Q and the.
Okay, we're going to derive this equation now. So you see that that was a good point. You see this equation has P bar, okay, but this equation has just bubble point pressure, or has a different case, or you have QA, okay. So to know the QA, now you have to come and do some derivation. So if you write it with me, that would be good because you need it. So you have the similar IPR curve. Okay. So here is going to be bubble point pressure. Bubble point pressure. And here it's going to be your P average visible pressure. And if you have this over here, this is going to be your QB, and this is going to be your QA. Okay? So this point over here, we call it C. And at C, your Q is Q prime. Okay? So we're gonna, this is the same thing as I wrote over there, but quite different because you don't have another point rather than just the bubble point pressure. So you write it down and you say at point C, okay, first we assume, so let me give you this one. This point, which is point C, it is slightly after the single phase flow. As you can see here, the slope has not changed much because you don't have many of gas bubbles evaporate out. Okay? So the first assumption that we should have is that we assume that slope is the same as this straight single phase line. Okay, this is the first assumption that you have. Second one, you can write your Q prime as Q minus QB. So your Q minus QB is going to give you the Q prime at this point. Okay, now that you have it, let's write down the Vogel's equation. So you have Q prime. So remember when I told you use Vogel's equation, then you're in the two-phase zone. Now you're in the two-phase zone. But like I told you, it's slightly after the bubble point pressure. Okay? Now that's why you can write Vogel's equation. Q prime over QA. So your Q max is your QA right now. You see why? Like I told you, you just think that everything happens after the bubble point. So if everything happens, you disregard this section. That's why your QA is this part over here. Does it make sense?
You said that Q max is the QA.
QA.
It's here. Instead of Q max, you see before the Q max is
At the- Okay. So let me make it simple. When you talk about Vogel's equation, you're just thinking about a section that it is in the one-phase flow. So this Q that you see over here is due to the single phase, right? But this whole thing, that if it could reach to, is called the maximum Q for the Vogel's equation. That's why I am deriving an equation that can relate this section, which is a single phase, to this section, Okay? Yeah.
Just to be clear, what is Q prime exactly?
Q prime, again, is the okay. So let's say your Q is over here, or your Q prime is over here. Okay. So your Q is going to be this much. That's why you minus it to the QB.
Okay.
Okay. Okay, so you write down so this point over here is slightly after the PB. That's your Q prime is a small amount. Okay? But if it was here, the Q prime would have been more observable. Okay? But now we just want to derive something that you guys are required to do it. Otherwise, you don't know what it means. So you write the, let me finish up with the Vogel's equation. So you write down Vogel's equation at that point, and let's get the reverse slope of this equation. Or what I mean is, let's get the derivative of above equation as a factor of PWF. Okay. So QB is going to be here multiplied by 2PB minus 1.6 PWF TB, and this is going to be 2 over here, right? So there's nothing here. So actually it is 1.6 multiplied this factor, okay? So when you get a derivative of Q prime based on the PWF, you come up with this equation, okay? So there is another assumption that you can use. You can say PWF at this point is the same as PB, P bubble point, because it's very close, right? So you have the assumption that PWF at that point is the same as P bubble point. Okay, so if you write it down this way, you're going to come up with an equation, which is going to be in this one. Does it make sense now? You know how we derived it? Do you have any questions? So let me flash back again. At this IPR, okay, the first section is a section that is in single phase flow. The second section, it starts for the Vogel, which is the multi-phase flow. As of right now, we are writing Vogel's equation to derive a relation that we're going to end up to, and we use this point over here, which is slightly after the bubble point pressure. So we are writing Vogel's equation for that. Okay, and we just do simple math to get the slope over here. Okay, this is not a slope, but this is dq prime over dpwf. Okay, so one assumption that we set over here, we said that the slope over here is the same as the slope over here. This value that you have over here is the reverse of your slope. Okay, so to write it down. So let's write down the slope at single phase section. So what is the slope as a single phase, or let's call it a reverse? So is QB over P bar minus PB, right? Does it make sense? So the slope here, actually the slope will be PWF minus P prime divided by QB. Okay? So we reverse it and we multiply by a minus number. So in that case, it's going to be equal to your dq prime dp WF. Do you agree? So do you agree with what's going on at this point? Question? Yes.
I'm sorry, but where did DQ prime minus where did PWF come
Come from? Look at this equation.
from?
Okay? Get the derivative of this equation when you put QA in this section based on your TWF. Let me do it as a y. Okay, y equal to 1 minus 2. So PB is just a number, so it's not a variable. So PB minus x, PB 2. Okay, so we want to have dy over dx. It's going to be minus 2 minus 2 multiplied by 1 PB minus 1.6 and x PB2, right? Okay, this is the same.
Okay.
Okay, so but here, so you have the QA you multiply here, that's you multiply by QA over here. You see, it's the same as derivative. So we said it's logical. That slope over here is the same as the slope at this point. So you have another relation. A slope at the single phase, reverse of the slope multiplied by negative value, you're going to understand it, is equal to the slope at that specific section because they are very close and you can make that assumption and it's going to be correct. Okay? So it's going to be QB minus. Now instead of this over here, okay, now we write this one over here. Okay? So it's going to be minus QA. Okay? And we further go and we can write QB over QA equal to 1.8 PB P minus PB. So this is the main equation I wanted to rewrite. Okay? No, this is not it yet, but this relation I wanted to get. So in this relation, you have QB, you have QA, you have this schematic over here that you can see each parameter, and you have PB and you have P bar. This is another relation. Okay? So now that we have these relations, just use it. So you remember we wrote Q prime over here, but we don't want any more Q prime. Either we want to have QE or QA, and that these two, because that's only variables that we want to see in our equation. So we said, what is Q prime? We said Q prime is Q minus QB. So we're going to write mu Vogel. So we're going to say Q minus QB, which is the Q prime, divided by QA, equal to 1 minus 0.2 PWF PB minus 8.8 PWF PB2, which is the same as what we have wrote over here as of right now. But at this moment, let's simplify further, okay? So we're going to break this division over here. So Q over QA minus QB over QA equal to 1 minus 0.2 TWF PB minus 0.8 TWF PB2. We didn't do anything yet. We just expanded it. We don't have Q prime anymore. This is just a function of QB and QA. So now that we have this, just remember, just look. Where is it? Okay. Let's call this equation 2. This equation 2 actually gives an expression, okay, for QB over QA. You see over here? And by using equation 2, so we call this equation 3. We can write equation 3 as, so we have this, this value over here. Q over QA equal to 1.8 TB minus PB plus 1 minus 2 PWF over PB minus 0.8 PWF PB squared. So this equation is what we needed. So what is the good thing about this equation? In this equation, we don't have any QB. Okay? Because, you know, I would say the production rate at the single phase flow, you don't need it. Because you're already past the point that you want to actually drive your IPR. So you don't need it. So based on that derivation of that relation that I showed you, which is over here, okay, we put it down in the Vogel and got this new equation. This new equation is the same as this equation, which is just a simple mathematical calculation. Okay? So you see, there is one. This is a point that I wanted to make. There is one Vogel equation. This is not Vogel. This is Vogel. So how do we get this? By simple mathematical derivation. That's this over here, okay, is the same as this guy. Okay, here. So remember, when you multiply this, PB is going to be cancelled by PB. So 1.8 is going to be plus 1. It means a minus sign. No, it's okay. When you multiply it, it has a minus sign. Okay? So if you go further away, simple math, it's going to get into that equation. Okay, is it clear? If it's not clear, I'm not going to move to the next question.
Yes, is the plus 1 supposed to be there?
Yes. Yeah, because here. Just trust me on this one. If you go home and you derive it yourself, you're going to find that it's correct. Because I derived it right before class. So make sure it's correct. Okay, the reason that we went through this difficulty of deriving this equation was because I wanted to show you there is one Vogel equation. But you might not be able to use it directly because your reservoir pressure is above bubble point. But there's no problem. You see over here, even though your pressure is above bubble point pressure, your average reservoir pressure, still you can use Vogel, which is this equation.
So we want to use that when it's above this.
Yeah. Let me put it in a strict statement. If you have your reservoir pressure above a bubble point, okay, you should use this equation. But if you have your average reservoir pressure at or below bubble point, you just simply use it over here. Make sense now? Yes.
So we won't use the opportunity index for analytical, we'll use Vogel.
Okay. This is how I want to let you know. That's a very good question. So this equation that we discussed over here, what part of this IPR can you draw it with? So this equation, okay, when we talk about Vogel, it is multi-phase flow. Don't talk about single phase. This is a very important fact. So, toward your question, this equation, okay, the Q and the PWF is going to give you the relationship from over here to here. You don't have the productivity index for this section. The place that you use the productivity index as a slope, okay, is over there. I should reverse slope. Is for that section. So let me discredit one of my slides. Here, so I got this from economist book, one of the references of Virginia. It's not me. The guy who's dead, by the way, who got this IPA curve as if you have the Zulu steady state single phase at the pressure of 0. Some might say BS, but I don't say it because the guy is dead. So this is just hypothetical. Okay, this is just hypothetical. Because at some point, at 0 temperature, zero pressure, of course, you're going to have gas evaporate out. So basically, upon your question, in order to draw IPR, there is a section that you can encounter bubble point, gas, and Vogel equation that you have to use. That's continuous line of the single phase is going to be continued again by Vogel.
So do you always use Vogels, like, even if it's, like, there's like all those different ways you can do the IPR, like Hagedorn, Brown, and all that, they all use Vogel equation? And use similarly?
Okay, so we have Fetkovich as well.
Uh-huh.
We have Fetkovich and Vogel.
Okay.
I mean, as far as I know, you have also Fetkovich in your slides, which is very simple than this one. So, but what I've heard is Vogel people are using a lot, well more than Fetkovich. Does it answer your question?
Yeah.
Okay. So let's get to the important part. That okay, which one of the part of the Vogel equation you're going to have question in your exam? How will be the question? Okay, so okay, let me go to the questions because we don't have much time. So let me tell you how. Okay, so in one case, like for Vogel questions, you have one data point. Someone says at Q equal 200, you have the PWF as, I don't know, 1,000 psi. Okay, find everything else. And you should be given the bubble point. So if you have it, you have this number here, and you have this one over here for that 1 point, and you have your PB, so you can get the QA. And the next question that they're going to ask is that, tell us what will be the production rate at the pressure of 900 now. Okay, so this one is going to be the only unknown. Why? Because we got it from the one data point that was given, that you calculated the QA. So you put the PWF, it was given, PB was given, and QA was calculated from the previous data point. Now you can get the Q. Does that make sense? So let's do this example now. Okay, so I know that I don't have time, so I wrote it down here. So exactly what I said. So you have a Q given as for one data point. Please write it down. You have the PWF for this Q that was given. Okay? So your bubble point pressure was 3,000 psi, also given, and your average level pressure also was given. Okay? These are all the information that you have. So the main question will be, after having 1 point of Q and PWF, you should be able to calculate the whatever production rate at given PWF. Does it make sense? So I'm going to explain it how it's done. So exactly what I said. So you wrote down, okay, just please, just listen to me at this point. Just take note that what is the status of your average reservoir pressure. Average reservoir pressure, if it is below bubble point, you are in heaven. You just use the Vogel equation. Yeah, so you see, I just took note of average reservoir pressure. So after doing so, to put the equation at the right equations, you have to memorize this one as well. Those three equations you should already memorize it. So you write it down, everything is going to be known, you get your QA. You have the PWF over here, you have the PP over here, you have the average reservoir pressure here, and you have the Q over here, you get the QA. Okay? The next question is QM. What is QM? QM is the ultimate maximum production rate, single phase plus multi-phase.
And QA is just the double, just the two phase.
So QA is the two-phase.
Okay.
So you already have your QA, but what is QB? For QB, you use the previous equation that we derived. You remember? Okay? So again, everything over there is going to be known, QA, PB, P bar. You get the QB and the Q max, ultimate max, it's going to be 288 at this point. Okay? So the next question, yes?
I'm confused for the please note the P is greater than the bubble point pressure. If you're at QA is at
Okay.
multi-phase, then wouldn't your pressure be below your
Yes.
bubble point?
I'm happy that you asked. What is this symbol for?
Average?
Average reservoir pressure, right? And I said, the whole difficult version of the Vogel is for when you have your P bar above your bubble point pressure. Okay? This equation, this question was given because of the known information that was given by Dr. Mali. You can tell that your P bar is more than your bubble point pressure. Now that you know, okay, this approach is used. Okay? So at this point you have QB, you have QA, you have PB, and you have P bar. Whatever they ask you, either they have to give you the Q or the PWF to actually calculate the other one that was not given. That is not given. So at this point, yeah.
What did you say QM was again?
Is-
QM. QM.
QM.
Yes, what you said was.
QM is this. QM is QB plus QA.
Oh, okay.
Okay? So now that you have everything, in this part, you're going to be calculating your Q at the pressure and buttonhole pressure of 1000. You put this over here, everything here now is going to be known, just Q is the unknown, and if you calculate and you get your production rate. Does it make sense? Just use this level. So you don't have PB anymore, right? You don't have PB. Because you're already below it, and who cares what the PB is? Okay, so are you done?
So we use that.
Okay, let me give you an example. Okay? So your P bar is at this point, which is below PB. So P bar is at here. If the question in 2000, so the P bar was 1800. Okay? Just use this one. It's
For the Q max.
yeah. So Qmax, okay, the Qmax, since your P bar is already here, you don't have such thing as QB anymore. Okay? Your Qmax is your QA. So I just want to let you know this. Not many people tell you about this fact that your P bar is above your PB. How to solve it. Okay? But you should know it because it's going to be wrong if your P bar is above bubble point and you put it in here and everything is going to be correct. So let's move on to the next question. It's simple again. Okay? Which is the question for your question name? Muriel. So this is a question of productivity index. Okay? So here in this question, again, your PWF at this point plus your P bar both are above the bubble point. Okay? So it simply is telling you that this point that over here that we was actually measuring and calculating is over here, the given. Just look at it here. So PWF is 3000, bubble point is 2000. Okay. So you use productivity index for the given Q and PWF. So your given Q is 200, PWF is 3000 psi. You put it down, you get the productivity index. You put the productivity index, okay, at this point. Okay, so you put the productivity index at that point and you get QB. So how you get the QB? The Q over here is QB. And you already have the PWF, PI, productivity index. And you have the bubble point. So all you have to do is just put it into this equation. Okay, you have to just put it. So you have the productivity index, you put it here, and then you can get the Q now. Is it clear? Clear? Okay. So now that you have the QB, okay, so the question asks you to give the PWQ or production rate of the PWF of 1000. 1000 is below the bubble point, so you should know the QA and QB. You should know the QA. Why? Because QA is here. Then you should know it. You just know the QB for now. But the relation that we derive has the QB over here and QA related together. Everything else here is known. So by this you get a QA. Then you have QA, you just simply put it in your right equation and get the Q at the PWF of 1000 psi. Question? This could be one example. Just, so if you get a degree in mathematics, Department of Mathematics, like master's, the question, for example, one of my friends got his master's in mathematics, and all the five final questions derive this, nothing else. But we're not in math department. So for this question, the given point that was telling you that you have the key PWF of 1 point as this was in the region of single phase flow. This equation?
No, equation
It's okay. This one is actually the relation between single phase and multi, because you have QB and QA.
So it don't matter if it's
Yeah. It's just a relation. If you have all the parameters there and your P bar is above your P bubble point, you get to use that. So, yeah.
So for the two examples you talked about for being above bubble point, right? For the two examples, what would it look like?
No, the other one, the given point was below bubble base. This one is above. This one is above. Okay, I know that it might be too much information out of right now. Just write it down. I can assure you that when you go home, you're gonna understand.
For the first one, it says B is above bubble point. For the question,
Okay, this equation, when it is the case, then this is the case, the last equation, okay, then we want to know the TWF of less than the bubble point. Okay? So here,
Well, okay, I thought that.
if you want to get the information or the data from here, you don't have to use any of these. But when it is over here, then we have to use that one. What one? QA? QA is after. Just let me say, guys, my office hours is Mondays before class, if anybody want to come, or you can email me, make an appointment so we can meet up. Okay?
I have a question. Are you missing that lot of that?
Yeah. But when you use this equation, that your average threshold is below also the bubble. If the average threshold is not, I'm sorry, P bar is above it. If it is less than the bubble, just do this simple.
So like,
There's no Qmax minus the Qmax.
it's like the easier feeling of working.
Okay, no questions? Yes.
Now you start working on it, you're just like.